Imagine holding the literal blueprint of a human life, just suspended right there at the end of a micropipette.
Right. It's a profound image.
And you're fully aware that, like, a millimeter tremor in your hand or even just a 1-degree drop in the ambient room temperature could entirely erase a family's future.
Oh, absolutely.
You aren't just looking at cells, you are holding paused timelines. And, looking at this massive stack of sources you sent us, the clinical guidelines, the laboratory standard operating procedures, qualitative research, it's wild.
Yeah, it really paints a different picture, doesn't it?
It really does. It becomes immediately clear that the modern IVF laboratory is, well, it's nothing like those automated black and white diagnostic factories we usually envision.
Not at all.
So, welcome to this deep dive. You, our listener, gave us a formidable mission today. We are going to map the murky, microscopic gray zones of clinical embryology.
I'm so excited for this.
We're stepping completely away from the sterile mechanical perception of the lab, right? We really want to confront the genetic and operational realities of reproductive science.
And it's such a fascinating landscape to explore because you're right. The embryologist operates in this incredibly high-stakes shadow world.
Yeah.
They are completely physically isolated from the patients. They're working behind secure, locked doors in these heavily filtered clean rooms.
Almost like a vault.
Exactly like a vault. Yet the physical expression of their daily work has these massive, echoing human consequences.
Right, the stakes are just astronomical.
They are. And when we synthesize the operational data in these sources, what really emerges is this portrait of stewardship.
Stewardship, I like that word for this.
Yeah, because quality control in this environment isn't just, an administrative checklist. It's an active, binding, moral commitment to the biological material in their care.
Wow.
Every single log, every temperature check, every calibration of a micro-manipulator, it's all a layer of that stewardship.
Right. So think of the embryologist almost like a master architectural restorer.
Oh, that's a good way to look at it.
Right. Someone who has been trusted with the delicate original blueprints of a priceless historic landmark. They have to maintain the structural integrity of those lines with absolute uncompromising engineering precision.
Exactly.
And they do this knowing that any microscopic miscalculation, any tiny deviation from the protocol completely alters the physical reality of the house that will eventually be built.
It's a staggering burden of responsibility. It really is.
And scanning through your notes here, it's clear that this intense stewardship starts at the absolute beginning of the cellular journey, right at the evaluation of the unfertilized egg, the oocyte.
Precisely, the oocyte. And even at that initial bench assessment, the level of observational precision required is immense.
Because they're looking at it before anything has even happened, right?
Right. When the embryologist first isolates that oocyte, they are making immediate critical assessments about its meiotic spindle and its maturation status.
Okay, so what exactly are they looking for?
Well, they are looking to see, is this oocyte arrested at the M1 stage?
Meaning it's not ready?
Exactly. Indicating it's still meiotically intermediate, it can't be fertilized yet.
Mm-hmm.
Or they're looking to see if it has extruded that first polar body and reached the M2 stage.
And M2 means it's ready to go.
Yes, meaning it is genetically prepared for fertilization. And these are incredibly subtle morphological distinctions under the microscope.
I can imagine, just tiny visual cues.
Very tiny. But getting that M1 versus M2 assessment right, that is the foundational data point for the entire cycle.
But to really get to the heart of the sources you shared with us, we have to look at the most complex, the most fiercely debated data these scientists actually interpret.
Oh, absolutely, the later stages.
Because ensuring an M2 oocyte fertilizes is really just the prelude. The real friction, the real diagnostic muddy waters happen when we start reading the genetic roadmap of the blastocyst days later.
Yeah, day 5 or day 6.
Right. Which brings us directly into the cellular gray zone of pre-implantation genetic testing, specifically PGTA.
What's fascinating here is how rapidly the scientific consensus has had to evolve, just based on the exact papers sitting in front of us.
Because it used to be viewed a lot more simply, right?
Oh, totally. For a long time, there was this myth of the flawless crystal ball. The assumption was that taking a trophectoderm biopsy gave you a definitive black and white snapshot of the embryo's chromosomal competence.
A simple pass or fail.
Exactly. But as these recent longitudinal studies show, the biological reality of a day 5 or day 6 embryo is inherently dynamic. It is not static.
Okay, let's unpack this.
Yeah.
Because reading through these PGT protocols, the physical mechanics of the biopsy itself seem to create, a massive spatial vulnerability.
Yes, spatial is the perfect word.
Right, because we are taking a laser, we're breaching the zona pellucida, and aspirating maybe 5 to 10 cells from the trophectoderm.
Just a tiny sample.
But we are strictly sampling the cellular lineage that is destined to become the placenta, right? While leaving the inner cell mass, the actual embryonic disc that becomes the fetus, completely untouched.
That is correct.
So if the trophectoderm and the inner cell mass can have totally divergent karyotypes due to, post-zygotic mitotic errors, isn't the entire premise of PGT fundamentally relying on a proxy that might be lying to us?
It's an incredibly educated proxy, but yes, you hit the nail on the head. It is still a proxy.
Wow.
The spatial disconnect you're highlighting is the exact root of the diagnostic dilemma in this field.
Because the placenta cells might not match the fetal cells.
Exactly.
Yeah.
The cells of the trophectoderm usually have a very high concordance rate with the inner cell mass, but biological systems are prone to mitotic non-disjunction. Errors happen.
Right, biology is messy.
It is, and when those errors happen post-fertilization, you end up with what these papers define as mosaicism. The blastocyst essentially contains 2 or more genetically distinct cell lines.
So your biopsy might pull a mixed bag.
Yes. Your 5 to 10 cell biopsy might pull 3 aneuploid cells, meaning abnormal, and 2 euploid, or normal, cells. Yeah. You are left staring at a literal genetic mosaic.
So if we've been operating under the assumption that genetic testing is this definitive crystal ball, how does a lab director even begin to handle a sequencer output that essentially shrugs and says maybe?
It was a massive challenge for the field.
Because if you have this microscopic cluster and the chromosomal data indicates it's a mosaic, early protocols basically just discarded them.
They did.
For years.
They just assumed that any aneuploid presence was a complete systemic failure of the entire embryo.
They did, but that approach completely failed to account for the astonishing resilience of early cellular life.
The embryo fights back, essentially.
It really does. The research you provided on embryo self-correction is paradigm shifting. An embryo isn't just passively writing out its genetic programming. It possesses active mechanical surveillance systems.
Well, wait, how does a 5-day-old cell cluster actually identify and neutralize a chromosomal error?
It's mind-blowing. Does it just, starve the bad cells out?
It's actually a combination of incredibly sophisticated mechanisms. If an embryo with a mosaic cell population continues to divide and implant, we see evidence of active marginalization.
Meaning it pushes them aside.
Exactly. The developing system essentially recognizes the altered metabolic signatures or surface proteins of the aneuploid cells. And it physically pushes them out of the inner cell mass lineage.
So it kicks them out of the fetus part.
Right, relegating them entirely to the trophectoderm, the placenta, where their chromosomal imbalance is much less likely to be fatal to the overall organism.
That is wild.
It gets crazier. In other cases, the embryo triggers selective apoptosis.
Programmed cell death.
Yes, it activates programmed cell death pathways specifically in the aneuploid lineage. It essentially forces the corrupted cells to self-destruct so they don't compromise the viability of the whole.
Wow. So it just cleans house.
It cleans house.
Yeah.
Because of this built-in biological wisdom, a mosaic embryo can absolutely yield a perfectly healthy, genetically typical child.
It's like discovering that a corrupted zip file on your computer actually contains its own internal antivirus software.
Oh, I love that analogy.
Right. It actively isolates the bad lines of code, quarantines them to a folder that doesn't matter, and allows the main executable program to run flawlessly. That is mind-blowing.
It changes everything about how we view early development.
But I have to push back here. Because if the embryo can self-correct, and the trophectoderm biopsy might just be capturing the quarantine cells that the inner cell mass already rejected.
Yes, the discard pile.
Right. How do you make a safe clinical decision? I mean, you can't just guess that the embryo is going to fix itself.
You absolutely cannot guess. And that realization that biology operates in this dynamic, shifting gray zone is exactly what forced the laboratory and clinical fields to create these concrete frameworks.
The rules of engagement.
Right, the data-driven frameworks we see in your sources. The lab cannot function on biological optimism. They require rigorous categorization to safely manage the potential transfer of these mosaic embryos.
Right. which brings us to the prioritization scales outlined in these international guidelines.
Exactly.
High standard laboratories are leaning really heavily into the quantitative data from the next generation sequencing. They aren't treating all mosaicism equally.
Not at all. The clinical actionability comes down to the precise percentage of aneuploid cells detected in the biopsy amplicon.
The exact ratio of good to bad.
Yes, as well as the specific chromosomes involved. Broadly, the guidelines divide these results into low-level mosaicism and high-level mosaicism.
Okay, looking at the data tables here, low-level mosaicism is generally classified as an aneuploid footprint of roughly 20% to 40% within the biopsied sample.
Correct.
And the clinical outcomes for this tier are actually surprisingly robust, aren't they?
They really are. The longitudinal data shows that embryos in that 20% to 40% mosaic category demonstrate highly favorable ongoing pregnancy rates.
That's amazing.
And critically, the miscarriage rates are statistically comparable to euploid or fully normal transfers in many cohorts.
So it's a real option.
Absolutely. If a patient's cohort yields no fully euploid embryos, a low-level mosaic is no longer considered a failed result. It is a primary, viable consideration for transfer.
But then you cross that 40% threshold, right, into high-level mosaicism, where the biopsy shows 40% to 60% of the sample is aneuploid.
Yes, that's where things get much more complicated.
The tone of the guidelines shifts dramatically here. The statistical risk of developmental arrest, implantation failure, or early pregnancy loss spikes.
It does. Transferring a high-level mosaic requires an incredibly careful, highly individualized clinical evaluation. And this raises an important question about how we translate this dense cellular data into human reality.
Right, because at the end of the day, there's a patient waiting for this news.
Exactly. The lab's role is not to act as a paternalistic gatekeeper. The embryologist reading the sequencer output does not dictate who gets to attempt pregnancy or which embryo is quote-unquote worthy of transfer.
That's not their job.
No. Their ethical mandate is strictly to provide the exact, unvarnished genetic coordinates.
They provide the raw map, but they don't dictate the route the patient takes.
Perfectly said.
But think about the patient sitting in the consultation room. You're looking at a couple who has endured, years of the physical, financial, and emotional attrition of IVF.
It's exhausting for them.
It is. They finally get to the blastocyst stage, they run the PGTA, and the data comes back as a high-level mosaic.
A devastating moment of uncertainty.
Yeah. So how do you bridge the gap between the cold, hard molecular statistics of a 50% unemployed cell rate and the desperate, very human hope of a successful pregnancy?
That is the exact intersection where high-integrity clinical care operates. And it is exactly why these protocols mandate multidisciplinary genetic counseling.
So you bring in an expert to translate.
You have to. You cannot simply hand a patient a lab report with a mosaic percentage and ask them what they want to do.
Yeah.
A certified genetic counselor has to sit down with them.
To deconstruct it all.
Right, to deconstruct the exact chromosomal involvement. Because not all chromosomes carry the same risk. They have to ask, is it a segmental mosaicism? Is it a whole chromosome mosaicism associated with a viable syndrome, like trisomy 21?
Or is it something fatal?
Exactly. Or is it a lethal aneuploidy that will almost certainly result in a first trimester loss? The counselor translates the raw laboratory data into a transparent matrix of risk.
So patient autonomy is preserved, but it's an autonomy armed with extreme scientific context.
Yes. The lab provides the molecular reality, the counselor provides the clinical risk matrix. But the ultimate choice of whether to transfer that embryo rests entirely with the patient.
Always.
Always. It's about deeply respecting the patient's right to try, while fully ensuring they aren't blinded to the biological odds of that trial.
As your sources highlight, not every embryo is destined for immediate transfer.
Right. Many go straight to storage.
Whether a patient has a successful first transfer, or they generate a large cohort of euploid embryos, or maybe they are doing fertility preservation for oncology reasons, those remaining blastocysts have to be secured.
They do.
And this shifts the profound responsibility we've been discussing away from the microscope and the sequencer directly into the physical infrastructure of the long-term storage facility.
The cryovaults.
Yeah.
This is the permanent sanctuary of the laboratory.
Reading through the standard operating procedures for these vaults, it is intense.
Well, wild, isn't it?
It really is. It's like managing the world's most high-stakes bank vault. But instead of guarding static assets like gold or bearer bonds, you are guarding paused biological timelines.
That analogy is incredibly apt. When you stepped into the liquid nitrogen storage facility, you were surrounded by these massive dewars holding thousands upon thousands of tiny cryostraws.
Just rows and rows of them.
Yes. Through the process of vitrification, the intracellular water of these embryos has been replaced with cryoprotectants.
So they don't freeze and shatter.
Right. They have been plunged into liquid nitrogen, crossing the glass transition phase without forming lethal ice crystals. They are resting in complete metabolic suspension at minus 196 degrees Celsius.
It's basically science fiction.
It really is. Thermodynamically, time has stopped for them. But guarding them requires a fortress of legal, administrative, and physical guardrails.
Because the inherent friction here is that while the embryos are suspended in time, the patients who created them are not.
Exactly.
Life outside the door keeps moving.
If we connect this to the bigger picture of clinic management, we hit what the legal literature in your stack calls the custody dilemma.
The custody dilemma.
Yes. Laboratories are the custodians of biological material that carries immense moral, emotional, and legal weight. But what happens when the human element becomes chaotic?
Which it always does.
Always. What if the couple goes through a highly contested divorce? What if one partner passes away unexpectedly? Or what if the patients simply ghost the clinic? They change their contact information, move out of the country, and just stop paying their annual storage fees.
The abandonment protocols in these sources are actually fascinating because you have a vitrified embryo that technically belongs to a patient, but the clinic has no way to reach them, and the storage bills are compounding.
It's a nightmare scenario for a lab.
Without a rock-solid legal framework, the lab would just be paralyzed, right? Storing assets indefinitely with zero authority to act.
Exactly. Which is why high-standard clinics cannot and do not operate on assumptions or post hoc legal maneuvering.
They have to figure it out early.
They figure it out before anything happens. The protocols dictate that explicit, legally binding consent and disposition agreements must be executed before the first dose of stimulation medication is even administered.
Wow, so before day one.
Before a single oocyte is retrieved or fertilized, the entire legal destiny of the potential embryo is mapped out on paper.
They are essentially enforcing a biological prenuptial agreement.
They have to. The documents must exhaustively detail exactly who holds the executive rights to the genetic assets in every conceivable scenario.
Like every edge case.
Right. If there is a death, does the surviving partner have unilateral right to reproductive use, or are the embryos to be discarded?
And in a divorce?
In a divorce, are the embryos donated, destroyed, or awarded to one specific party? If storage fees lapse for a specified number of years and certified mail is returned undeliverable, what is the default legally protected action the clinic can take?
The administrative foresight required is just immense.
Is a massive undertaking.
But beyond the legal and administrative paperwork, there is the sheer physical logistics of the vault itself. I mean, you have tens of thousands of microscopic straws submerged in opaque liquid nitrogen.
You can't even see them through the nitrogen.
Right. So how does a lab actively prevent what the operational papers call regulatory drift? How do you guarantee that a specific straw in a specific goblet belongs to the right patient a decade after it was vitrified?
Regulatory drift is the silent killer of laboratory integrity. It really is. It's the slow compounding of tiny, seemingly insignificant administrative errors over time.
Just a millimeter here and there.
Exactly. To combat this, the SOPs require continuous, grueling audit structures. It isn't just about reading a label.
It's much deeper than that.
The lab must verify that the physical location of a microscopic straw, its specific color-coded cane, within a specific goblet, inside a specific numbered canister, within a designated liquid nitrogen tank, perfectly and seamlessly matches its digital coordinates in the clinic's electronic medical record.
Because if a straw is misfiled during a chaotic thaw day, or if liquid nitrogen exposure degrades a poorly affixed label, or, if someone's handwriting blurs a 7 into a 1.
The consequences are catastrophic.
It's unimaginable.
You're looking at the potential of the wrong embryo being warmed and transferred to the wrong patient. It is the absolute nightmare scenario that keeps lab directors awake at night.
Here's where it gets really interesting to me, because human eyes and human hands are fundamentally fallible, right?
Yes, we make mistakes.
No matter how many manual audits you run, embryologists are human beings working in high-stress, high-volume environments. They experience cognitive fatigue, they get distracted.
It's unavoidable.
To maintain a true zero margin for error environment across thousands of microscopic assets, you can't just mandate that your staff, pay closer attention.
That never worked.
You literally have to engineer the capacity for human error out of the physical workspace.
And that is exactly what the modern laboratory does through what is effectively an administrative shield.
The administrative shield.
Yes, they utilize strict verbal double witnessing protocols, deeply layered with advanced electronic witnessing systems, or EWS.
The tech specs you provided for these EWS setups are incredible. Walk us through how this administrative shield actually functions at the bench, like in practice.
It's a localized, highly specialized surveillance net. We are utilizing radiofrequency identification RFID chips and high-resolution, laser-etched barcodes that are physically integrated into the plastics of every single dish, tube, and cryo straw used for a specific patient cycle.
So everything is digitally tagged.
Everything. But the real innovation is the workspace itself. Specialized RFID antennas are built directly into the heated stainless steel stages of the laminar flow hoods where the embryologists manipulate the cells.
So the physical desk is actively reading the identity of the dishes resting on it.
Exactly.
Okay, let's stress test this with a near-miss scenario. Say an embryologist is working under the hood. They have a sperm preparation tube from patient A. By some fluke of cognitive fatigue or distraction, they reach to the incubator, grab an oocyte dish belonging to patient B, a completely unrelated cycle, and bring it onto that same heated stage.
Okay.
What mechanically happens?
The system response is instantaneous. The moment that unmatched RFID tag enters the invisible frequency field of the antenna on that workstation, the EWS detects the discordance.
It knows right away.
Immediately. It triggers a harsh, audible alarm throughout the laboratory. But more importantly, it physically locks the interface.
Wait, it locks them out?
Yes. The monitor on the micro-manipulator flashes a hard stop, and the embryologist literally cannot proceed to log the step. The system completely paralyzes the workstation.
Oh, wow.
Until a senior laboratory director manually intervenes, investigates the mismatch, and documents the override. It is a hard technological wall against human error.
That is a brilliant piece of fail-safe engineering. It's like an invisible force field around the genetics. But wait, let me challenge this for a second.
Sure.
In aviation and medical administration, there's a well-documented phenomenon called automation bias, right?
Oh, yes.
If you have a desk that physically screams at you every time you make a mistake, doesn't that inherently breed complacency? If I know the RFID will catch my error, why wouldn't I, as an exhausted embryologist, just subconsciously start relying on the alarm instead of my own eyes?
It's a very real concern.
Does the tech actually make the humans sharper, or does it make them lazy?
That is a highly astute pushback, and it's a vulnerability that human factors engineering has studied extensively in these labs. If the EWS becomes the primary check, the system will eventually fail.
Right.
The technology is designed strictly as the ultimate backup. The true primary shield is the immovable culture of mandatory verbal double checks. The tech does not replace the human conscience. It audits it.
So the human-to-human verification is still the required first step.
Absolutely. The protocol demands that before the embryologist even introduces that dish to the RFID field, they must have a second, senior embryologist physically break their workflow and stand next to them.
So they have to stop what they're doing.
Yes. The primary embryologist must verbally read the patient's name, date of birth, and unique medical record number out loud from the dish.
Out loud.
Out loud. And the witnessing embryologist must visually verify those exact details against the physical cycle paperwork, verbally confirming the match. The electronic system is only there to catch the impossible 1 in a million failure of that human interaction.
It's overlapping layers of armor, really. The legal consent matrices, the manual spatial audits, the verbal double checks, the RFID lockdowns.
It's all necessary.
All of this intense infrastructure exists to guard these embryos until the patient's family-building journey reaches its natural conclusion. But looking at the final section of your sources, eventually that journey does end.
It does.
A family achieves the number of children they desire, or they make the difficult decision to cease treatment. And that brings the lab to the most delicate, ethically fraught operational protocol of all.
The final disposition.
Yes, the final disposition of the surplus embryos remaining in the cryovaults.
When a family's reproductive journey is complete, the laboratory transitions from being a guardian of potential, to a facilitator of closure.
That's a beautiful way to phrase it.
The protocols outline 3 strictly regulated ethical paths for these surplus embryos. The patients must make this profound choice, and the laboratory is bound to execute it with absolute precision and respect.
Let's break down these 3 paths. Looking at the guidelines, Path 1 seems functionally akin to adoption, though clinically it's referred to as compassionate donation to another couple.
Yes, Path 1 allows a patient to donate their vitrified embryos to another individual or couple facing intractable infertility.
But it's not as simple as just handing them over, is it?
Not at all. The logistical and physiological hurdles here are massive. Because the embryo was not originally created with the intent to donate, the FDA and international regulatory bodies require retroactive, exhaustive infectious disease screening of the original genetic parents.
That makes sense.
It requires complex legal clearance to officially transfer ownership and often mandates deep psychological counseling for both the donors and the recipients.
It's a huge commitment.
It is an arduous path, but it allows one family's surplus to become the missing piece of another family's puzzle.
But, not everyone wants their genetics out in the world, raising a child they will never meet. Which leads to Path 2, donation to scientific research.
Yes.
For a couple whose entire reproductive journey relied on cutting-edge science, is this a way to sort of feed their embryos back into that scientific loop?
It is a profound way to leave a scientific legacy. Under Path 2, the patients consent to transfer their embryos to approved, peer-reviewed research facilities.
What kind of research are we talking about?
These embryos might be used to derive new embryonic stem cell lines, or to study early cellular differentiation and developmental biology.
So really foundational science.
Exactly. The data gleaned from these donations directly drives the next generation of reproductive breakthroughs. It helps researchers understand the mechanics of the exact mosaicism we discussed earlier.
Oh, full circle.
Right, and ultimately improves the efficacy of IVF for future patients.
And then there is Path 3, compassionate discard.
Yes. This is the choice when a couple does not wish to donate for reproductive or research purposes, but instead requests that the laboratory thaw the embryos and allow them to naturally cease cellular division.
For a couple who fought that hard, we are talking about patients who endured years of negative tests, the physical toll of ovarian stimulation, the crushing financial burden, just to get these exact blastocysts.
It's an incredibly heavy choice.
It is. These embryos are the physical manifestation of their struggle and their success. They represent the hypothetical futures of children they will never meet. How does a laboratory ensure that executing Path 3 doesn't just feel like throwing away a biohazard bag?
That's a vital question.
How do the protocols honor the immense emotional weight of that request?
By entirely removing it from the realm of routine operations, the execution of Path 3 is never handled as an administrative clear-out.
It's separated completely.
Yes. The SOPs dictate that a compassionate discard is a profound, highly formalized procedure. It is executed with an absolute maximum level of administrative verification and deep institutional respect.
So mechanically, how is a compassionate discard actually executed in the lab?
It begins with a verification shield operating at its highest sensitivity. Multiple senior embryologists must independently confirm the barcodes, the patient identifiers, and the explicitly signed, notarized consent documents before a single dewar is even open.
They triple-check everything.
At least. Once verification is absolute, the physical process is incredibly quiet. The specific cryostraw is pulled from the liquid nitrogen and brought into room temperature air.
Wait, they don't place it in warmed culture media?
No. The embryologist simply allows the cryoprotectants to naturally dilute at room temperature. Without the precisely warmed, nutrient-rich culture media required to sustain metabolic function, and exposed to the osmotic shifts of the thawing process, the cellular division gently and naturally arrests.
It just stops.
The biological timeline stops.
And reading through some of the qualitative studies here, many clinics don't just do this in the dark. They actively integrate the patient's emotional need for closure.
Yeah, that's becoming much more common.
Some protocols accommodate patient-led ceremonies or allow the couples to be physically present in a private room adjacent to the laboratory during the exact window of time that discard is occurring.
It provides a tangible spatial reality to say goodbye to the potential those cells held.
That's incredible.
It is. And this raises an important question, one heavily featured in the burnout studies you provided, about the unseen emotional toll this exacts on the people executing the procedure.
The embryologists themselves.
Yes. You have an embryologist who dedicates their life to optimizing the genesis of cellular life. And on a given Tuesday, their scheduled procedure is to deliberately end the biological timeline of an embryo that someone desperately prayed for just a few years prior.
The emotional whiplash is profound.
It truly is.
The psychological weight of that must be staggering. Let's dive into the physical reality of the embryologist's day-to-day, because the environment itself sounds punishing.
Oh, it's not for the faint of heart.
They are working in these dark, temperature-controlled, heavily filtered clean rooms. The ambient noise is just the hum of the incubators.
Very isolating.
Right. They spend hours hunched over microscopes, executing micro-manipulations where a fraction of a millimeter means the difference between successful fertilization and catastrophic failure. The physical and visual tension alone is a recipe for high-stakes fatigue.
And unlike other high-stress medical professionals, say, a trauma surgeon who saves a patient and watches them walk out of the hospital, the embryologist, is the ultimate hidden scientist.
They never see the end result.
Rarely. They carry the immense emotional gravity of a patient's entire reproductive future on the tip of their pipette, but they almost never get to see the human realization of their labor.
They're just behind the glass.
Right. They hand a microscopic cluster of cells over to the physician through a window, the transfer is performed, and the embryologist turns back to the darkroom. They live entirely in the realm of potential.
And as the sources point out, these laboratories are ultimately businesses, right?
They are.
They are driven by intense metric tracking. How does a clinic balance that emotional burden with the pressure to produce flawless key performance indicators? Lab directors are tracking blastocyst conversion rates, fertilization rates, warming survival metrics.
That's a lot of data.
If the entire business model relies on maintaining pristine success rates, isn't there a massive operational danger of just treating the patients like statistical data points?
That is the greatest ethical hazard in the field. There is a very real temptation to protect a clinic's published success rates by turning away complex, low-prognosis cases.
Just to keep the numbers up.
Exactly. But true ethical stewardship, the kind outlined in the most rigorous guidelines here, demands that optimal KPIs be balanced with individualized, compassionate care.
How do they do that?
A high-integrity laboratory embraces the difficult cases. They offer transparent, honest science to a 43-year-old patient who might only yield 1 or 2 oocytes.
They don't turn them away.
No, they do not view those cells as a threat to their metrics. They view them as a patient's best, and perhaps only, biological hope.
But you cannot sustain that level of deep, individualized care if your scientific staff is completely burned out and emotionally blunted.
Which is why the resilience strategies outlined in these operational papers are so critical.
What do those look like in practice?
High-performing clinics mandate structured rotation systems, so no single embryologist is anchored to the highest stress procedures, like biopsies or discards, day after day.
They mix it up.
Yes. They integrate mandatory mental health decompressions and team debriefs to process the clinical losses. Because the ultimate goal is to ensure that every time an embryologist sits down at that heated stage, their mind is sharp and their empathy is completely intact.
Like an air traffic controller, but instead of tracking planes on a radar, you're tracking the literal genesis of human lives in Petri dishes. You have to be dialed in.
Because in this field, the empathy is the operational equal of the physics.
So what does this all mean? When we look at the incredible stack of sources you gave us, we've mapped an entire universe that exists within a single drop of culture media.
A whole universe.
We've moved from the shifting genetic math of a mosaic trophectoderm to the cold, legal realities of the cryovaults, to the profound solemnity of a compassionate discard, all the way to the mental resilience of the hidden scientist at the bench.
And if we synthesize the core philosophy running through all of these documents, it is that the modern IVF laboratory is not a factory designed to conquer nature.
It's not about brute forcing it.
No. It is a highly engineered environment designed to gently, precisely support it. The laboratory is a magnificent bridge built between advanced cellular physics and human hope.
To everyone listening, whether you are a clinician looking at these protocols, a patient navigating these gray zones, or simply someone fascinated by the mechanics of life, the reality is that every single child born through this science is a testament to a vast, unseen network.
A huge network of dedicated people.
It is a symphony of embryologists, geneticists, and nurses working in perfect harmony behind locked doors, utilizing extreme technical precision to turn a long winter of waiting into a lasting spring.
It is a remarkable scientific legacy.
It truly is. And I want to leave you with one final thought to mull over, circling back to the very beginning of our dive into your sources. Think about that mosaic embryo.
The self-correcting one.
Exactly, a microscopic cluster of cells completely invisible to the naked eye, resting in a plastic dish. If a day 5 embryo possesses the inherent biological wisdom to actively survey its own structure, to recognize its flaws, and to self-correct its own genetic errors against all statistical odds just to survive, what does that teach us about the profound built-in resilience of human life long before we ever take our first breath?